Okay, speaking of isotopes, we want to take the atomic mass of an element. You'll notice that when we look at an element on the periodic table, it always features some decimal value. And you're probably thinking, wait, mass number should be a whole number because there's only protons and neutrons that we're talking about. But isotopes exist. And because isotopes exist, they're going to be various kinds of the same element present. Therefore, in order to calculate the average of all the different isotopes for an element, we do what's called the weighted average. And the weighted average of this is the weighted average of all the naturally occurring isotopes of an element. And natural is the key. Isotopes can be artificially made by fusion and fission reactions, but these are only naturally occurring isotopes of the same element. So how do we take the weighted average? Well, the formula for this is we take the mass of that particular isotope times its percent abundance or natural abundance. This will be provided for you in the problem. We add that to the mass of the second isotope and multiply it by the percent of the second isotope. And we keep doing that and divide by 100. Alternatively, you'll have to convert the percent value to a decimal, and you remember how to do that probably from your math courses. If we have a percent, all we have to do is move the decimal 2 places to the left. So 75% simply means 0.75. So we can write the percent abundance as 75% divided by 100, or we could simply write it as 0.75. And these are some more examples that show you how to convert percents to decimals. I'll give you a chance to look at this before we move on so you become familiar with percents versus decimals. Okay, let's start some problems. The table below gives the atomic mass and the abundance of 2 naturally occurring isotopes of boron. Here we have boron 10 and boron 11. Which numerical setup can be used to determine the atomic mass of the element boron? Remember, we have to take the weighted average, and that's done by taking the atomic mass multiplied by the abundance and either converting this percent to a decimal or dividing the whole thing by 100. Okay, numerical setups simply show how the atomic mass was calculated. So if you look, the only correct answer is answer choice 1. And how did we get this? It's mass times the percent, 10 times 19.9, plus the mass of the second isotope, 11 times the percent, 80.1. And because these are in percent values, we have to divide everything by 100. All of these answer choices are incorrect. Let's try another problem. Again, we're given a table with atomic mass and the abundance of 2 naturally occurring isotopes of bromine this time, bromine 79 and bromine 81. We're given their masses and their abundances. Which numerical setup can be used to calculate the atomic mass of the element bromine? Notice that we're given decimal values here, and we're not dividing by 100. That's because the percents here have been converted to decimals. So think about what the correct answer is in order to calculate the average. Okay, we see that the only correct answer would be the one where the mass is being multiplied by its percent in decimal form. We have 78.92 times 50.69%, which is equivalent to 0.5069. We move the decimal places 2 places to the left, plus the atomic mass of the second isotope times its percent. But the percent is converted to decimals, so we have 0.4931. Therefore, the answer 3 is correct. Let's try another problem. Here we're given another table. You can see that the Regents likes giving you tables, and it asks you to calculate. It should provide the numerical setup that can be used to calculate the atomic mass of gallium, which has 2 different isotopes, and it gives you their percent abundance this time and the atomic mass. Okay, we see that the percent abundances are written in decimal form. So the only one that shows the correct answer would be the percent abundance, 0.6011 times 68.926 right here, and 0.3989 times 70.925. These problems become very simple if you just remember to multiply the percent times the atomic mass and divide everything by 100, or convert these percents to decimals. Let's try another problem. The atomic mass of an element is the weighted average of the atomic masses of, and again, this is just a definition question. Please note that answer choices include the words naturally, which means occurring naturally in nature, and artificially, which means man-made. Okay, weighted average is calculated by taking the average of the atomic masses of the naturally occurring isotopes of the element, not the artificial ones. Next problem. Naturally occurring gallium is a mixture of isotopes that contain 60.11% of gallium-69. It gives you the atomic mass, and 39.89% of gallium-71 with the corresponding atomic mass. Which numerical setup can be used to determine the atomic mass of naturally occurring gallium? Okay, it's just percent times mass. But we have to convert the percents to decimal. So this would be 0.6011 times 68.93. So the answer choice 3 is correct, plus 0.3989 times the mass, 70.92. Okay, this time it provides you a table, and it's a short response, and it asks you to show a numerical setup for calculating the atomic mass of potassium. We're given 3 different isotopes of potassium: potassium 39, potassium 40, potassium 41. We see percent abundance and their atomic mass. You apply the formula correctly, this won't be an issue. Okay, you should have come up with the following. Average is equal to 0.9326 times 38.96 plus, move this decimal 2 places over, 0.0001 times 39.96 plus 0.0673 times 40.96. Alternatively, you could have just multiplied these percentages times the mass, do it for the second one, do it for the third, add them all up, and then simply divide everything by 100. Either one of these answers is correct. Please note that questions asking for numerical setups do not require calculation. They simply want you to show their work. So please do not go through the hassle of trying to calculate this number, especially if there's a chance that you might get this wrong as a result of some sort of miscalculation. Just show your work. Last problem. Which numerical setup can be used to calculate the atomic mass of the element chlorine? Again, if you remember that the percents have to be converted to decimals, the only possible answer choice is answer choice 3, 34.97 times 0.7576 plus 36.97 plus 0.2424. Okay, hopefully this was helpful, and thank you for watching.